Hello students, today we will be doing the numericals on the machines chapter. So let us see the formulas and the concepts that will be applied while working out the numericals of this chapter. There are certain technical terms which should be clear to you. First of all, it is the mechanical advantage, which is defined as the ratio between the load and the effort. Effort is the force which we apply while making a machine to work, and the load is the force which we have to overcome. So first of all, we write the formula for mechanical advantage. We will be taking mechanical advantage always as m dot A. It is a ratio between the load and the effort. So we write it as L by E. L stands for load, E stands for effort. Then the next important technical term is velocity ratio. Whenever a machine will be used, there will be the displacement of the load and the effort, and there will be a certain time taken for doing it. So displacement by time will become velocity. So that is velocity ratio will be a ratio. Velocity ratio, we will be writing it as V dot R. So it is the velocity of the effort by the velocity of the load. So we write velocity of the effort by velocity of the load. But since the time taken for the movement of the effort and the load will be the same, so that is why the time will get cancelled when we write displacement by time. So we always will be using the formula for velocity ratio as displacement of the effort by the displacement of the load. These two terms should be remembered, it will be used a lot. Another important thing to be remembered about velocity ratio is this. That is, once a machine has been designed, its velocity ratio remains fixed. It will not change. A very important thing to be remembered. But mechanical advantage can change because as the machine is being used, there will be friction increasing, wear and tear will lead to increase in friction. So as a result, mechanical advantage of a machine can change as we are using it over the time, but velocity ratio will remain fixed. Next thing to remember is this part. Whenever we are using any machine, work output and work input will be the same in an ideal machine, but it is impossible to get an ideal machine, then work output will always be less than the work input. So we should know what is work input and what is work output. So first of all, for work input, so work input, we know work is force into displacement. So the force applied in input case is effort. So effort multiplied with the displacement of the effort. This is your work input. Then we will get work output. So work output case will come load multiplied with the displacement of the load. So if we are having an ideal machine, we can always apply that work input and work output is equal. But if it is not an ideal machine, in practical case, it will not be equal. Then a very important term comes now is efficiency. So efficiency is meaning is how much effective that machine is for us. So it will be decided always based on what is the ultimate work output as compared to the work input. More better the work output, we say that the efficiency is more. So it is a relationship between the work output and the work input. So we have efficiency as work output by work input into 100. So if we are doing in 100, we are going to get efficiency in terms of percentage. If you don't use 100, efficiency will be in terms of fraction. We can leave it in both the ways, but it will be better if we bring it in percentage. So in an ideal condition, when these two are equal, efficiency will come as 100%. Okay, but in actual condition, it's not going to happen like that. It will always be less than 100%. So this is one relationship of efficiency. By using work output, work input formula here and of mechanical advantage and velocity ratio, we come to another formula for efficiency. I am writing here the symbol of efficiency also. So in that case, if I apply these formulas over here and simplify it out, I will get efficiency as mechanical advantage by velocity ratio. If it is required to be brought in percentage, then with this you can multiply with 100. I will not show another formula based on this by cross multiplying, because you can substitute the values of the known thing and find the unknown one. So these are some of the technical terms which will be used a lot in the first part of the numerical. First part of machine also has levers in it. So we should understand the different types of levers and the relationship there, what will be required. So here we will be seeing about levers. So first of all, the first class lever, okay. In first class, you should remember that the effort at one end, fulcrum at the middle, and the load at the other end. So when fulcrum is in the middle and the effort and the load at the two other end, that is your first class lever. Then the second class, we have the fulcrum here. Then we will be having the load here, and the effort has to be applied in the upward direction for it to be lifted up, load to be lifted up. So when load comes anywhere in between the fulcrum and the effort, we call it as the second class lever. So fulcrum comes here, then there will be a load. So this load has to be lifted up, and for that you require effort to be applied in the upward direction. So when effort is in the middle, we call it as the third class lever. There is an easier way to remember that. We tend to write the one which is there in the middle. So if I remember like this, flea means fulcrum in the middle, first class lever, load in the middle, second class lever, effort in the middle, third class lever. Now, when we have a lever, if we know the load and the effort, we can find the mechanical advantage by this way. But the load arm and the effort arm also help us in finding the mechanical advantage. By applying the principle of moments, we can get the relationship to find the mechanical advantage using the load arm and the effort arm. So here mechanical advantage has another formula, which is effort arm by the load arm. So this is a very important relationship where you can easily get the mechanical advantage in case of lever. Now for lever, one more thing we should know, depending upon the value of mechanical advantage and velocity ratio, we can categorize those machines into different types. So we will be seeing that now. So if we have in a machine mechanical advantage coming greater than 1, or we know velocity ratio value and we get that as 1, then that machine is categorized as force multiplier. So you should remember, this is very important. You get the value of mechanical advantage greater than 1 or velocity ratio greater than 1, that machine is called as a force multiplier. Now, what happens if I am getting mechanical advantage less than 1 or velocity ratio less than 1. In this case, it will be a speed multiplier. That machine will help you in increasing the speed. So we write it as speed multiplier. Now, it could be possible also that load and effort, or the displacement of the effort and the load is same. In that case, mechanical advantage will come as equal to 1. So what happens then? Mechanical advantage equal to 1 or velocity ratio equals to 1. Then such a machine will only help us in changing the direction of the effort to a convenient direction. So we write here changes the direction of effort. So you should find out the value of mechanical advantage or velocity ratio value, and then you can categorize whether it is a force multiplier, speed multiplier, or simply it just changes the direction. So I hope all these formulas which are there, you have taken a note of it, so that we can now proceed to the numericals and solve all the numericals of exercise 3A. So now we start with the numericals. The number one numerical, let us see. It says a crowbar of length 120 centimeter has its fulcrum situated at a distance of 20 centimeter from the load. Calculate the mechanical advantage of the crowbar. You have to first know here in this numerical that a crowbar is a first class lever. So because it is a first class lever, so I need to show the fulcrum in the middle and the load and the effort at the two ends. So I am showing here load, fulcrum and the effort. So it says the fulcrum is situated 20 centimeter from the load. So this becomes 20 centimeter. Then the crowbar is of length 120. So 120 is this entire length is 120. We know mechanical advantage is effort arm by load arm. So now we need to find the effort arm first of all. So we go to write here effort arm is equal to that entire length 120 minus this 20, which is equals to 100 centimeter. Now we can write mechanical advantage equals to effort arm by load arm, and so the values are effort arm is 100, load arm is 20, dividing it we get 5. Remember, mechanical advantage is a ratio, so it has no unit. Do not do the mistake of writing any unit when you are finding mechanical advantage as well as velocity ratio. So this 5 is your answer. Now let us take a look at second numerical, which says a pair of scissors, okay, has its blades 15 centimeter long. So it is the blade where the load, the thing to be cut, is kept. So the blade length will become the load arm, while its handles are 7.5 centimeter long. So it is the handle from where we apply the effort. So the length of the handle will become the effort arm. What is its mechanical advantage? So a very direct sum to the numerical. Only we should be clear about which one is the load arm and the effort arm. So we write here mechanical advantage as effort arm by load arm. So effort arm, as I told, is from the handle part. So that is 7.5 centimeter. And this one, the load arm is 15 centimeter. We know that 17 7.5 into 2 will give us 15. So it will cut and give us 1 by 2, which I can write as 0.5. This is my answer. No unit for mechanical advantage. So with this, we come to the end of this second numerical. Let us take a look at the third one. A force of 5 kgf is required to cut a metal sheet. So we require a force of 5 kgf to cut a metal sheet. A pair of shears are like scissors, but here the length of the handle is greater. Okay, so that is to be remembered. A pair of shears for cutting a metal sheet has its blades 5 centimeter long. So the blade where the load arm will be there is 5 centimeter, while its handles are 10 centimeter long. So this becomes the effort arm. In a shear, the effort arm is always greater than the load arm. So it acts like a force multiplier. What effort is needed to cut the metal sheet? So what effort we have to find? So this is what is given to us as load. So if we mention the values here, which one has what value, and let us write it. So first of all, I will write here load as 5 kgf. Then this part 5 centimeter is my load arm. And this becomes 10 centimeter becomes the effort arm. We can do this sum in two ways. I can find the mechanical advantage by using effort arm and load arm. And then again I apply the mechanical advantage formula as load by effort. Since mechanical advantage is already known, I can get the effort because load is given there. But there is another way to relate. In a lever, we can always apply the principle of moments and get a relationship, that is load into load arm will be equal to effort into effort arm. This formula I have not written in the beginning. If you want to make use of this formula, you can note it in that formula place. This formula, load into load arm equals to effort into effort arm. So this comes by the principle of moments, and if you remember this, it saves the steps of working out. So we know the load here as 5 kgf, load arm as 5, effort we have to find, and the effort arm as 10. So we get effort equals to 25 by 10, that is equals to 2.5 kgf, because the load was given in kgf, so we are writing effort unit also in terms of kgf. I hope you all have understood this relationship, how to apply, and please kindly again I repeat, note it down in that formula part. It will make your task easier. Let us come to numerical 4, which is a numerical based on the diagram. So let us follow the question, understand it. Figure 3.15 below shows a lever in use. To which class of lever does it belong? So this is the lever given. Load here, effort here, fulcrum in the middle. So it becomes the first class lever. Then AB is 1 meter. So if AB is 1 meter, this is as 1 meter. Okay. Then it is told AF is equal to 0.4. So this is 0.4. So this is the load part given. This is the fulcrum. So this becomes load arm. So load arm is 0.4. From the fulcrum to the effort will become the effort arm. So 1 meter minus 0.4 meter. You can easily make out that this will be 0.6 meter. So we know the load arm, we know the effort arm, we know the load, we have to calculate the effort. So let us do the working of it. First of all, in the A part, they had asked us to which class of lever does it belong to. So we will write here, that is class 1 lever. Okay. Now let us come to the B part. So entire length was 1, load arm is 0.4. So I will go to write effort arm will be 1 minus 0.4, that is equals to 0.6 meter. So now we know the load arm, effort arm and the load. Let us go to find the effort by using load into load arm is equal to effort into effort arm. So load to us is given as 15 kgf. So let us write 15 into load arm is 0.4. Effort we have to calculate, and effort arm we had got as 0.6. So effort will come 15 into 0.4 by 0.6. So 15 into 4 by 6 after decimal one place. So I have removed in both the places. So 2 2s are 2 3s are 3 5s are. So 5 2s are is 10 kgf is our load. This is the answer. Let us come to the next numerical, which is number 5. Let us understand the question. A man uses a crowbar of length 1.5 meter. So the entire length of the crowbar is 1.5 meter to raise a load 75 kgf. This becomes the load by putting a sharp edge below the bar at a distance of 1 meter from his hand. The sharp edge below the bar will become the fulcrum, and it is 1 meter from his hand. So it is the hand from where we apply the effort. It becomes the effort arm. Draw a diagram of the arrangement showing the fulcrum. So we have to draw the diagram of it first and mark all these points, fulcrum, load and effort, with their symbols, and state with the directions also. So we have to show the direction which we have been showing till now in all the numericals. State the kind of lever it will be. Calculate then in the C part the load arm, the effort arm and the mechanical advantage and the effort needed. So let us proceed one by one. So first, for the A part, we have to draw the diagram. Okay. So we have the fulcrum in the middle. So this part is there. So this is the load part. Fulcrum will come in the middle. In a crowbar is a first class lever. So we are drawing in that way. And then we will require the effort here. So this is all with the direction. Load is acting downward. So because the first class lever, we need to pull it down with our effort to raise it up. So A part is done. Okay. State the kind of lever it is. So B part, class 1 lever it is. Then coming to the C part, we will see all the values. But before that, let us put all the values which are known. A crowbar is of 1.5 meter. So 1.5 meter. This is completely is 1.5 meter. Then it is told putting a sharp edge below the bar at a distance 1 meter from his hand. So effort will be applied with the hand. So this is the sharp edge. So I am getting 1 meter from here till here is 1 meter. So that becomes my effort arm. So now we can calculate the load arm, effort arm. So first of all, for the load arm, so load is here, form fulcrum is here. This will give me load arm. So it will be 1.5 minus 1, 0.5 meter is the load arm. Then we go to calculate the effort arm. So effort arm is fulcrum to the effort, which is already given to us 1 meter. Then we have to find the mechanical advantage in the third part. So we write mechanical advantage equals to effort arm by the load arm. And so effort arm is 1 meter. Load arm is 0.5. So you get it as 2. Then we have to find the effort. Because we have the mechanical advantage and the load of 75 kgf already known, so I will apply another formula of mechanical advantage, that is load by effort. So we have mechanical advantage here as 2, load is 75 by the effort. So I can write now effort is equals to 75 by 2, and 75 you divide it by 2, you get it as 37.5 kgf is your answer. So various things were asked, but it was very easy. Step by step, if you do, you easily get it. I hope you are understanding the numericals which I am explaining. If you are getting benefited from it, do remember to like the video and also subscribe to my channel. So let us move to this numerical number 6. A pair of scissors, remember scissor is a first class lever, is used to cut a piece of cloth by keeping it at a distance of 8 centimeter from a rivet. So where the rivet is the point where the joining is there. So load is kept, the cloth which is being cut is the load is kept at a distance 8 centimeters. So this becomes the load arm and applying an effort of 10 kgf. So effort which is applied from the handle is 10 kgf at a distance 2 centimeter from the rivet. So where the effort is applied is 2 centimeters. So that becomes the effort arm. Find the mechanical advantage of the scissor and the load offered by the cloth. So it means you have to find the load here, and how does the pair of scissors act as a force multiplier or as a speed multiplier. Once we know the value of mechanical advantage, we will easily be able to comment upon this. So let us write the things which are given to us. So cloth is kept at a distance of 8 centimeter. So I am writing here, for all I will write this load arm is equal to 8 centimeter. Then effort is 10 kgf. And then it is fingers are kept at a distance 2 centimeter from the rivet. So effort arm is equals to 2 centimeter. So we know the load arm and the effort arm. Let us go to find the first one, the mechanical advantage, by using the formula effort arm by load arm. So effort arm we have 2 by 8. So 1 by 4, if you know that 1 by 4 on divided will give you 0.25. So this is your first answer, mechanical advantage, so no unit. Okay. Now let us come to the second part, the load which is offered. So we know this another formula, mechanical advantage is load by the effort. So we have got here as 0.25. Load we have to calculate. Effort we had got as 10. So cross multiply. 10 multiplied with 0.25 will give you 2.5 kgf. So that finishes the second part. Okay. Now in the B part, how does the pair of scissors act, as a force multiplier or as a speed multiplier? Look at the value of mechanical advantage, 0.25, which is less than 1. So we can write the answer to it. Since mechanical advantage less than 1, therefore it is a speed multiplier. So you are able to now decide how it will be a force multiplier or a speed multiplier. Let us come to numerical number 7. I find this numerical a very good one to understand the concept of this topic. Let us see at the numerical. A 4-meter long rod of negligible weight, so we don't have to consider the weight of this rod, is supported at a point 125 centimeter from its one end. And a load of 18 kgf is suspended at a point 60 centimeter from the support on the shorter arm. The 60 centimeter, wherever you are supporting from there toward the shorter arm at a distance 60 centimeter. First, if a weight W is placed at a distance 250 centimeter from the support on the longer arm to balance the rod, we have to find the weight W. And then it says, if a weight 5 kgf is kept to balance the rod, now we don't have this W weight, we have a 5 kgf weight, we have to balance it. So where should we keep it? We have to find its position, and then it is asked to which class of lever it is. To do this numerical correctly, the diagram is very, very important. So try to understand the diagram properly. First of all, a 4-meter long rod is there. So this is my 0 part. This is my 4-meter part, which I will write as 400 centimeter. Okay. Now, understand what is being done. It is being supported at 125 centimeter from its one end. We can take that end anywhere, and 125 centimeter it is supported. So what I am doing is, I am writing here, so this is my 125 centimeter mark. So this side is the shorter part and this side becomes the longer part. Remember, this acts like the fulcrum. Then we come to load of 18 kgf is suspended at a point 60 centimeter from the support on the shorter arm. This is the support, shorter arm is this side. At a distance 60 centimeter, we are having a 18 kgf weight. So this is my 18 kgf weight at a distance of 60 centimeter. That is, this length is 60 centimeter. I have not written the unit there, 60 centimeter it is. If a weight W is placed at a distance 250 centimeter from the support on the longer arm to balance the rod, find the weight W. So from the support 250 centimeter on the longer part, so I am taking here is our weight W, which we have to calculate, and this is given to us as 250. From the support, that is the fulcrum, to this is 250. So this diagram I hope you have understood. Now we can easily apply that load into load arm equals to effort into effort arm and find this W. We can consider any one of them to be the load and the effort. Okay, because nothing is being mentioned here. Okay, so if I write here load into load arm is equals to effort into effort arm. So load I am considering this one as 18 into 18 into 60 is this length, equals to the effort is the weight W here, and the effort arm from the fulcrum to this part is 250 written here. So W will be equals to 18 into 60 by 250. I am cancelling out this 0 first. So I am getting 25 here. I will try to multiply with 4 and make it as 100 below. Okay. So I am multiplying with 4 so that it will be easier. So here I will be getting as 100, and if I multiply 18, 6 and 4, I am going to get that as 432. So I get 4.32 kgf. So this is my answer for this weight W, which was hung here, which we had to calculate. So this was the A part, which is done. Now in the B part, if a weight of 5 kgf is kept to balance the rod, now that weight is not there. Okay, now a 5 kgf has to be kept. So this weight will be pulling it downward. So I put it on that side at a distance of x. So I am putting that weight 5 kgf here, and I am considering this distance to be as x. So again we will apply the same thing. Okay, load into load arm is equals to effort into effort arm. So load is here 18 into 60, that part has not changed. Effort here, the weight is 5 and the effort arm is that distance x. So we go to calculate now. 18 into 60 by 5. So 5 12s are 12 8s is 96, 9 12 ones are 12 and 9 is 21. So 216 centimeter, which I can write it as 2.16 meter. So we get here this weight of 5 kgf from the support, it has to be kept at a distance of 2.16 meter. Then it is asked to which class or river it belongs. You know that fulcrum was in the middle. So the C1 answer is class 1 type. I hope this numerical based on the diagram has been understood. So whenever you get a numerical like this, try to get the diagram drawn properly. Let us see numerical number 8. A lever of length 9 centimeter has its load arm 5 centimeter long. So the entire lever is of 9 centimeter. The load arm is of 5 centimeter and the effort arm is 9 centimeter long. So you should get it here is that the length of the rod and the effort arm is the same. So effort will be completely at one end. Load arm is only 5 centimeters, so load will come in the middle, fulcrum will be at the other end. So load in the middle, remember it will become the second class lever. To which class lever does it belong? So as I told, it will be a second class lever. Draw a diagram of the lever showing the position of the fulcrum F and the direction of both the load L and the effort E. And then what is the mechanical advantage and velocity ratio if the efficiency is 100%? So we have, when the efficiency is 100%, you should remember it becomes an ideal condition, and in that case mechanical advantage and velocity ratio is the same. Then what will be the mechanical advantage and velocity ratio if the efficiency becomes 50%? Remember that mechanical advantage of a machine can change, but the velocity ratio remains the same. So that concept will get applied here. So let us see one by one all the part of it. First of all, I will try to get the diagram drawn, so that will make you to understand easily also to tell which class or lever it belongs to. So the B part, I am trying to do it first. The diagram, this is the entire length, so is 9 centimeter. This entire thing is 9 centimeter told. Then it is told that the load arm is 5 centimeter. So think I take the load here acting. So I should take the fulcrum here. This becomes 5 centimeter and the effort arm is given 9 centimeter. So I need to apply the effort here upward. Okay, that is 9 centimeter. This is becomes the effort arm. The length of the rod and the effort arm is the same. So you can see that load is coming in the middle. This is the fulcrum. Let me write F here. So I can write here it is class 2 lever. Okay. Now in the C part, what is the mechanical advantage? So I will write here effort arm by load arm formula, because we know these two values. Effort arm is, you can see, is 9 centimeter and load arm is 5 centimeter. 9 divided by 5 will give me 1.8. We are getting 1.8. This second class lever is always acting as a force multiplier, and that is by the value also shown. Then it is told velocity ratio if efficiency is 100%. Okay, when efficiency is 100%, okay, then we will always have mechanical advantage equals to velocity ratio. So we get velocity ratio coming as same 1.8 as the mechanical advantage. So now what is happening here, we have to find the mechanical advantage and velocity ratio if the efficiency is 50%. Now the efficiency has come to 50%. As a result, mechanical advantage will change, but velocity ratio will remain the same. So I am writing here, this is the D part. Since VR does not change, therefore velocity ratio remains as 1.8. Now efficiency is 50%. So let me write efficiency formula. Mechanical advantage by velocity ratio into 100. So efficiency is given to us 50%. So 50 is equals to mechanical advantage we have to find. Velocity ratio will remain as 1.8 into 100. So I get mechanical advantage 1.8 will multiply with 50 by 100. 50 2's is cancel. 1.8 divided by 2 will give me 0.9. Okay, so mechanical advantage comes as 0.9. So a very good numerical to keep you in this understanding that the velocity ratio does not changes, but mechanical advantage will change, and it depends upon the efficiency. I hope this numerical is clear to you all. Let us see the next one, ninth one. It says in figure 3.16 below shows a lever in use. To which class or lever does it belong? Let us take a look at this. We have the fulcrum at one end, load in the middle, and effort at the other end. So we have load in the middle, and when load is there in the middle, you know it is a class 2 lever. Okay. Then it says without changing the dimensions of the lever, so nothing is changed, the magnitudes are not changed. If this load is shifted towards the fulcrum, okay, this load will be shifted towards the fulcrum. So what happens to the mechanical advantage of the lever? Means it has some mechanical advantage now. If this load is shifted towards the fulcrum, what happens to it? We have to comment on that. So let us write it and then follow the explanation also. So first of all, I will write here, it is class 2 lever. Okay, then to the B part, follow again. I explain, the question says that this load is shifted toward this side. So from here the load is being taken this side. So if I bring the load this way over here, so this becomes the load arm. Okay, so earlier the load arm was this much, I have taken that side, so it means load arm has got shortened. So if the load arm is getting shortened, what happens to the mechanical advantage? So to know it, let us see the formula. It is effort arm by load arm. So effort arm is not changing, it is fixed. The entire length of the lever is the effort arm. So whatever was the load arm here, if you know that it is there in the denominator, the load arm is getting reduced. So as the load arm is getting reduced, the mechanical advantage will increase. Okay, so another way to take a look, load arm is in the denominator, it means mechanical advantage is inversely proportional to the load arm. So if the load arm is being reduced, mechanical advantage is going to increase. Okay, so we write here, as the load arm is being reduced, therefore mechanical advantage will increase. So I hope this concept has been understood here. Let us come to this numerical number 10. It says in figure 3.17, this is a wheelbarrow shown to you all, okay, of mass 15 kg. So the mass of this wheelbarrow is 15 kg because the mass is given. So the weight of this will get added up to the load which will be kept inside it with a load of 30 kgf. So it has a load of 30 kgf with its center of gravity at A. So entire weight will be acting from here. The load also will be acting from here. The points B and C are the center of the wheel and the tip of the handle. This is the center of the wheel. So from here only you will be getting the fulcrum part. So this is the fulcrum. Okay, this is the fulcrum. The load is acting from here, and the effort will be applied in the upward direction. Okay, and then it is told that the distance AB, A to B, the distance is 20 centimeter. So you know that this will become the load arm. Okay, this will be your load arm. And then AC, A to C, so from here to here is 40. This is the effort, this is the fulcrum. So the effort arm will become 60 centimeter. So your effort arm will be 20 plus 40 is equal to 60 centimeter. Okay, so they are asking us to find the load arm, effort arm, the mechanical advantage, the minimum effort required to keep the leg just off the ground. So we have how much effort will be needed to lift it. So let us start with one by one. So the A part is asking the load arm. Load is here, fulcrum is here. So this is the load arm. So let us write load arm is equals to 20 centimeter. Then to the B part. B part says the effort arm, which I have shown here. I will just repeat it over here. Effort arm equals to 20 plus 40 equals to 60 centimeter. Then the C part, mechanical advantage, we can easily get when we know the load arm and the effort arm. So mechanical advantage is equals to effort arm by the load arm. So effort arm is 60, load arm is 20, dividing give us 3. Then minimum effort required to keep above the ground means the effort which we have to apply. So I will apply here mechanical advantage is equals to load by effort. Mechanical advantage, we know it is 3. Now the load part, again I will repeat, the wheelbarrow has a mass of 15, so it will become 15 kgf. I'm writing here your unit. The load is extra, that is 30 is there, so this will be 30 kgf, and the effort we have to find. So effort will become, this added will become 45 divided by this 3. So I require 15 kgf minimum effort to lift the wheelbarrow above the ground. Now let us come to numerical number 11, which says Ramesh went for fishing with his fishing rod. Identify the class of lever for a fishing rod. If a fish exerts a load of 10 Newton and the distance between the fulcrum and the fish is 1.5 meter and the effort applied is and the effort is applied is at 0.5 meter from the fulcrum, what is the force required by the fisher to pull the fish? You have gone through the chapter, you will know that a fishing rod is considered to be a third class lever. Let us see by a diagram. Okay, fulcrum is here, the fish over here is, this is the load. Okay, so it is told that fish is exerting a load of 10 Newton. Okay, this is 10 Newton load. This is the fulcrum part. So now the effort is to be applied. Okay, so effort will be applied, it is told, and the distance between the fish and the between the fulcrum and the fish is 1.5 meter. So this is 1.5 meter. Okay, and the effort applied is 0.5 meter from the fulcrum. So I will have to apply effort in the upward direction. This is given to us 0.5 meter. From here to here is 0.5 meter. Okay, so a fishing rod is a third class lever. So we have to mention which type of lever it is. Okay, so we write here class 3 lever. Okay, now we need to apply the effort which the fisher will be applying. Okay, so we go to apply load into load arm is equal to effort into effort arm. So load here is 10 Newton. Load arm is the entire thing, which is 1.5. Effort we have to calculate, and the effort arm is 0.5. So you know you will get effort as 10 into 1.5 by 0.5. You know 1.5 divided by 0.5 will give you 3. Okay, so that gives us 30. Here load was given in terms of Newton. So remember to write effort also in terms of Newton. So the fisherman has to apply an effort of 30 Newton to lift that, with that fishing rod, to lift a load. The fish weight is, which is 10 Newton. Let us come to the next one, numerical number 12, figure 3.18. This is the figure, shows of a lever fixed here. So this is the fulcrum, effort is applied in the middle, load is at the other end. So you quickly get it that it is a third class lever. State the principle of moments as applied to the above lever. We have been using this, that is load into load arm is equals to effort into effort arm. That is what will be written in that. To which class of lever does it belong? Already seen it is a third class lever. Give an example of this class of lever. We have so many of them. Okay, we have already seen a fishing rod, then a spade is there, fire tongs is there, sugar tongs are there. Any one of them you can write. Then the main numerical part comes here. If FA is 10 centimeter, so this part is 10 centimeter. So this is the fulcrum, this is the effort, so it will become your effort arm. Okay, then AB is 490 centimeter. This is your AB part. Okay, don't do the mistake of taking this as the load arm. Load arm is the length from the load till the fulcrum, so that will be 490 plus 10, 500 centimeter. It says calculate the mechanical advantage, so we have to get the mechanical advantage and the minimum effort required to lift the load. So we have to find the effort also. So let us answer it one by one. First of all, the A part, the principle of moment which we have applying here. So as said, load into load arm is equal to effort into effort arm. Okay, this is your A part. B part, asking which class of lever it is. As informed, class 3 lever. Okay, we have to write one more example of this. So I can write this example as any one of them. I am writing here fire tongs. Okay, fishing rod could have been written, a spade could have been written. Now coming to the C part, FA is 10, so this is my effort arm. So I will write here effort arm equals to 10 centimeter. Okay, we have to find the load arm as explained here. Load arm will be from the fulcrum to the load. So I will write here load arm equals to 10 plus 490 is equal to 500 centimeter. So now I can go to find the mechanical advantage. Effort arm by load arm. So effort arm is only 10 centimeter. This is 500. So zeros cancelled. We will get 1 by 50. I can leave it in fraction. Also, if I want, I can write it in decimal. So 1 divided by 50 will give you 0.02. So we have got the mechanical advantage. No unit required here. And this was the C first part. Second part, we have to find the minimum effort required. So for the second part, again I write mechanical advantage formula. Now I will write load by effort. Now mechanical advantage, I can use any of this, but you know fraction value will be better to be used. And then load is here 50 and effort we have to find. So cross multiplying, effort will give us 50 into 50 is 2500. Load was given in Newton, so we write here in terms of Newton. So the minimum effort required to lift it will be 2500 Newton. Coming to the last numerical of this part, okay, 13th one, a fire tongs has arm's length 20 centimeter long. So fire tong, we should quickly make out which type of lever it is. We have just now seen it is the third class lever. It is used to lift a coal of weight 1.5 kgf by applying an effort at a distance 15 centimeter from the fulcrum. From the fulcrum, the effort is at 15 centimeter. Find the mechanical advantage of the fire tong and the effort needed. So always better to get the diagram which makes it clear which is the effort arm and the load arm. It is a third class lever. So fulcrum at one end, effort will be there in the middle somewhere, but let me show the load first, and the load given is 1.5 kgf, and then it is told this is the entire length is 20 centimeter. So you know now that the load arm is 20 centimeter. Effort is being applied at a distance 15 centimeter from the fulcrum. So effort will be applied in the upward direction and it is told 15 centimeter. So effort arm is 15 centimeter. So now the diagram makes it clear what is your load arm and effort arm. We can apply the formulas and get it. First is to find the mechanical advantage. So mechanical advantage is equals to effort arm by load arm. So effort arm is here 15 and load arm here is 20. So you cancel it with 5, you get 3 by 4. 3 divided by 4 will give you 0.75. So your mechanical advantage we have got as 0.5. Now the effort needed, we can find it. So again, mechanical advantage is equals to load by effort. Mechanical advantage value I will substitute here is 3 by 4, will not take the decimal value. Load is 1.5 by effort. So effort will come here 1.5 into 4 and 3 will come down. So this if I reduce, I get 0.5. 0.5 into 4 will give me 2. Load was given in terms of kgf. So I go to write the unit here as kgf. This is my answer. I hope you have understood this. All the numericals are done. Hope you are benefiting it by my explanation. Again, I repeat, kindly like the video and subscribe to my channel, and do comment upon what are your other requirements. If you have any particular sum to be solved, please write it in the comment box. Thanks for watching.